Okay, so hello everyone. My name is Aryan, and for today, our topic is about entropy. And let me just give you an introduction to entropy right now. So, entropy is a measure of disorder or randomness in a system. It plays a fundamental role in the second law of thermodynamics. Understanding entropy helps explain the evolution of physical systems from gases to cosmic objects. So, entropy is a measure of disorder or randomness. Uh, or we can understand it as the quality of energy being more spread out. It's like if I have something, if I burn an incense stick right now at this point, someone will smell that incense stick on the other room, in the other room, and that is because of entropy, because the energy has spread out, the molecules have spread out, and the reason the entropy is increasing right now uh, goes back to the Big Bang due to the past hypothesis. So, the past in the past of our universe, what happened that the everything was very uniform. The energy was very uniform. It was distributed uniformly, and if we talk about that, it means that in our sense, like the positional entropy, the entropy was high. Uh, but in gravitational terms, what was it the case that all of the things are in a uniform place, uniform things. So that according to gravitational entropy is a very low entropy state. Because gravity just pushes in things, right? As you know, so that is why uh, the entropy is increasing in the universe because of the past hypothesis. Some historical background of entropy. This concept was introduced by Rudolf Clausius in the 19th century. It was initially developed to describe heat transfer and irreversibility. The term entropy derives from the Greek word entro, meaning transformation. So it was first developed by Rudolf Clausius in the 19th century to solve the problems of uh, steam engines. I think so. It's a story of France. There were few people who were trying to design more better and better his steam engines, but the maximum efficiency they could achieve was 2 or 3%, which was not a lot. And there were few people who tried making an 100% efficient machine, but they failed because, as we know, that energy tends to spread out. So some new people have also joined us, I think so. So thank you everyone for joining us. So and that is why Rudolf Clausius developed this concept of entropy. And there's he also wrote a research paper. You can check that out. I think so. The name was on the governing forces on heat. It talks about like these clauses, definition of entropy, like these things. So it majorly uh, checks the entropy change, and to get the entropy, we have to do something else. So let's begin with clauses entropy definition. So uh, clauses define entropy as the integral of heat transfer over temperature in reversible processes. Delta S is equals to Q by T. Uh, this integral is path independent for reversible processes. Entropy change quantifies the amount of energy dispersal in a system. So, like independent, what this means right now here is like if I want to climb something, I'll just give you an example. If I want to climb something like a mountain, uh, if it was state independent, we have to go like we have to follow the trails and everything. But in path independent, we just draw an imaginary straight line to it, because the destination is same. Here, the states, the things that happen in between don't matter. Okay. So, did everyone understand what is path independent? Aryan, did you understand it?
Not properly.
Okay. So, in path independent, we just go straight to the point, to the peak. But in state independent, we have to follow the trails and everything. So state, this entropy concept is path independent. We just go straight to the point, but in state dependent we have to follow everything the particles did in the way to getting that place. So did you get it now?
Yes.
Okay. What is reversible? Real world processes depend on measurable temperature gradients and friction. When energy flows across finite thermal gaps or ions experience electrical resistance, or heat inevitably escapes into the environment. This energy degradation creates random internal chaos because this stray heat cannot be recovered. Real systems naturally generate irreversible entropy. So, uh, in clauses definition, uh, in the upper part of that, there would have been an REV, or reversible process. So it treated as an a reversible process that can be changed, like water freezing to become ice and melting to become water. So he treated it as a reversible process, but in real life these things are not irreversible. And but the thing is that it still worked out because it was path independent. Okay, so ladies and gentlemen, do you have any questions? Sakshamana, Aryan, do you have any questions?
No.
Okay. Entropy of a gas. To calculate a gas's entropy change, we replace clauses heat variable with measurable properties. Added heat performs two distinct jobs. It raises temperature and expands volume. Therefore, the maths splits into a temperature part and a volume part, tracking energy dispersal across both atomic and spatial arrangements. So, I did not go on and added maths to it because this part was pretty hard for me to. So what to calculate the entropy of a gas, the entropy change, what we do is that we have two parts, the where when the heat raises the temperature, and the work done by the heat, which like the work done is expanding the gas. As you can see in the picture, it expands and contracts. So heat does that. If we heat an solid, it will go to a liquid state and then a gaseous state. So this is the entropy increase of a system. So it includes two parts: the heat, the temperature raised, the raised temperature, and the expanded volume. Joule per Kelvin. So the unit JK measures energy dispersal efficiency, not temperature rise. The joule represents the raw heat injected, while the Kelvin represents the existing thermal noise. Injecting energy into cold, quiet system creates massive structural disorder, yielding a high joule per Kelvin rating. And in this Hall system, the same energy causes negligible change. So, so what does this mean is that if we already add heat, the energy into a very hot thing, it won't create more special arrangements, right? But if we do that to a cold one like ice, it creates massive special arrangements and leads to more entropy. So this is what the joule per Kelvin measures. So Aryan, did you understand this concept?
Yes.
Okay. So, can you explain it in your words if you understood the topic so well? Okay,
When Joel, Joel per Kelvin is injected in something cold. No, when heat is injected in something cold, it uh, it makes thermal noise and creates a massive disruption while disordering by joule rating in a hot system.
okay. So I don't think so. You understood it very well. So let me give you a real life example. If I have a very clean order room and if I throw something in it to make it messy, what happens is that after some, like, if we look at the special arrangements, the room would be messy, but like it would be more messier than its original state. But if we already throw that specific object in an already messy room, it won't create much difference, right? So that this is what joules per kelvin measures. In higher messier rooms it's less, and uh, in cleaner rooms it's higher. So did you get it by this example?
Okay, it's like if we there is a dot, there's a dot of white paint in on a black sheet of paper, but if we sprinkle some of it, then it will look not much messier.
Okay, so you understood it. So I for the other people, let me just repeat his example. If I have a black sheet and if I put a paint on it, just one singular paint, it would be messier than its original state. But if I already have a very messy sheet full of color and paint, and if I drop another color on it, it won't create that much of a difference. So it was also a very good example by Aryan. So I think so everyone understood this topic, so we should move to the next one. Ludwig Boltzmann. So he's a very important figure in this concept. So Boltzmann revolutionized thermodynamics by reimagining continuous heat as a statistical game of colliding atoms. He proved that entropy isn't a mystical energy fluid but a measure of probability. This atomic approach sparked fierce 19th century debates with prominent established physicists who firstly denied the atoms even existed. So he was way ahead of his time. Had. So what he thought is that it's just logistics and statistics. So it isn't. He didn't use physics or stuff. He just used maths and probability stuff. So Aryan, I have a question for you. Why doesn't uh, why does heat flow from hotter to colder object?
Because the particle is moving.
Can you repeat?
I think because the particles are moving and transferring heat another to another.
Okay, so why does that happen only one way? Why doesn't it happen the other way? The heat from the cold transfers to the hot.
I don't know.
Okay, so do you want to do some maths? Uh, I can help you with the by understanding this using maths.
Okay.
Okay, so let's imagine that the hot and cold body are two objects, and these are two spheres, and there are ten particles in each in each square, and let's assign them something called heat. Heat. So let's assign them a property heat, and let's say that the colder one has three heat packets and the other one has maybe seven. And if we just do the maths, if we just calculate the number of, like if we combine them, make them one sphere where each of them had 10 spaces and 10 spaces, they would have 20 spaces, and the left and right, the left one has 3 and the right one has 7. If we just uh, okay, so uh, did you understand the specific the arrangements concept that I taught you earlier?
No, Aryan.
Okay, so if I have one particle in first box, let's cut them in 20 boxes each particular space. If I have one particle in one box and the other one in the let's say fifth block, and like a specific arrangement, was something in there, something in there, so that is called a microstate. So like it's like if you take a picture of that room, all of the specific particles are arranged in in that manner, and that is called an microstate. So that is just like a particular snapshot, a picture of that specific arrangement. So that is called an microstate. And if we want to calculate that, uh, like it would be something I can't figure it out. So if we just do the logistics and stuff, we'd find out that the left side with the cold box would end up with more energy packets, like, and we just took it with 10. In reality there are trillions and billions of particles, and as we increase the number of particles, like in our first case, the energy can move from cold to hot and hot to cold. Because of probability, it would be like something like it would be pretty high compared to real life. But in like speaking in real life terms, it contains trillions of atoms. So, and if we just do the maths, we'll figure it out that heat flowing from uh, hot to cold is more probable. So that is how he thought of this question. It's just a statistical game. So do you understand it, right? Do you have any questions? Saksham, Aryan, hello Aryan, are you here? Okay, so what? Let's get to the next topic, microstates. Okay, so the total number of available microstates determine the statistical weight of a given a macro state. Because a system samples its available phase space randomly, macro states containing the highest microstate count possesses the maximum mathematical probability of occurring, driving the systems toward peak entropy. So and microstate, uh, uh, I just explained, is a snapshot of a specific arrangement of particles in a box. And macro state, what is that? So and macro state is like the whole ground, the number of particles, number of spaces, the box. So that is my macro state. And the macro state with the most amount of micro states is the most probable one that we see in real life. So uh, ladies and gentlemen, do you have any questions? Okay, combinations. Microstate probability depends on its microstate count W. As particle numbers scale, the combination increases exponentially via binomial coefficients. Systems naturally drift towards macrostates with the largest macrostate pools. A thermodynamic equilibrium is simply the state of maximum mathematical probability where the system settles into the most common microscopic configuration. So it's something like that. To calculate an entropy of something, what we do is that we take the Boltzmann constant, which is about 10 raised to the power of minus 23 joule per Kelvin, and we take the uh, what we say the natural logarithm of the number of microstates. So, Aryan, do you know about what's an natural logarithm? Hello, Aryan. Okay, so you'll understand it better here. So, Boltzmann equation. So, Boltzmann linked macroscopic configurations directly to macroscopic thermodynamic entropy through his foundational equation S is equals to kV times the natural logarithm of W, which is the number of microstates. Here, S is absolute entropy and W is the microstate count. Boltzmann constant Kb acts as the scaling factor, converting pure statistical counts into real world thermodynamic units of joule per Kelvin. So, if we just do that, the logarithm is something like if I want to get the logarithm of 1000, it would be 3. So, logarithm is the inverse operation of 10 raised to the power of x. So, if I get the logarithm of something like 2, it would be something like that. And if I do 10 raised to the power of that answer, I'll get 2. So this is what is logarithm. So Aryan, do you understand it? Okay. So so logarithm they are in calculators. So so if you want, let's just take an example where we have a box and 10 spaces and 3 particles. So the entropy of that would be part, the number of spaces, which is 10 factorial, divided by the uh, number of particles, which is 3 factorial, and which would be and times the number of spaces available and the number of particles there are, which would be 7, wait, which we got 3000. And if I just put in the natural logarithm of that, we get 9. So it would be the entropy of that system is 9, uh, 9 times the Boltzmann constant, so which would be, I think so, 10 raised to the power of 22 something joules per Kelvin. So this is, I just gave you an example of the Boltzmann equation. So there are like finding the microstate. If I just gave you an example where particles don't stack, but in particles that do stack, the entropy is exponentially higher, like thousands of times. So this is like putting a thermometer in lava and calculating its temperature. But the next equation that will see like later in the presentation is a little different than this. It's like looking at a chimney and deciding its temperature, calorimetry. To find absolute entropy, scientists warm a frozen sample inside a vacuum calorimetry from near 0 Kelvin to room temperature. They continuously record heat capacity divided by temperature and plot the results on graph. The total area under this curve equals to the substance's absolute entropy. And Debye's P3 T cube law. Real instruments cannot reach absolute zero or measure accurately below roughly 10 Kelvin. To close this gap, scientists use Peter's Debye's rule, which states that a frozen solid's heat capacity drops proportionally to the cube of the temperature. So I'll give you an example of those two slides. Uh, so to calculate something's entropy by using the Debye's cube law, it has to be near 10 Kelvin or something like that. So let's say that I have the Debye's constant. There's something called as Debye's constant for a particular material is 0.03, and the Kelvin, the temperature at that point is 10. So we'll cube the temperature, which is T, and which will give us about 30 joules mole Kelvin. Okay, so after that, we divide that specific amount that we got, which would be the Cp, which is the heat capacity. So heat capacity, and that would be the total, that is be the specific heat capacity to increase something like 1 Kelvin. So we'll need that amount of energy to heat 1 Kelvin, to heat that material, like that specific gram or something mole by 1 Kelvin or degree, like that. So that is the specific heat capacity, and which we got that, and we'll just plug it into the equation. The entropy at that point would be entropy at 10 Kelvin would be 30, which is the Cp, the specific heat capacity, by 3, and we'll get 10 joules mole per Kelvin. And uh, if we like want to calculate, and if you want to calculate the specific material at 20 Kelvin. So we'll use calorimetry, and to find that, to use that, we have to find the Cp total, total one, the total heat capacity. So it would be Q by N times the number of the material, the amount of material times delta T. So delta T is the is like T2 minus T1, which is, let's say that I pulsed 1000 Kelvin joules into it, and it temperature increased by 10 degrees, 10 Kelvin. We'll get the difference of the kelvins, which will be 20 minus 10, which is 10, and that we'll just take that one mole and divide the 1000 by 1 mole times 10 Kelvin, which is 100 joule per mole Kelvin. And and after we got that, we get the entropy change. I don't think so. I've mentioned it here right now. So which would be the Cp, the heat capacity, times the natural logarithm of T2 by T1, and the T2 was 20 and T1 was 10. So it would be a heat capacity which was, we got 100 times, let me just calculate, times the natural logarithm of 2, which would be 0.69314 something. And if we just multiply that uh, by 100, we get about 70, and we just got the entropy change, which was 70. And if we just add the other one, like the specific material at 10 Kelvin, which was the absolute temperature, absolute entropy, which was about 10. So we'll get 80. We get we got 80 as the entropy. So so this is how we calculate. Like, we don't have to calculate. There's the scientists have already performed them. They are in specific tables. I don't remember the names. Molar, something like that. So we have given the entropy of every material there. We have already done the calculations. Now we are getting to the more interesting part of this presentation. But before that, Ladies and gentlemen, do you have any questions? Uh, Aryan, are you here? Do you have any questions? Okay, I don't think so. So, black hole challenges. A black hole is an object wrapped so densely that gravity warps space-time into an absolute one-way trap. Its boundary, the event horizon, marks the cosmic point of no return. Anything crossing this line is completely severed from our viewable universe, presenting a massive challenge to standard thermodynamic laws. So what happened is that when we discovered black holes, they were regions of such intense gravity that nothing could escape, not even light. So if you drop something into it, it's just lost to us, or has so it means the universe's entropy decreased. And there's something in, let me just say, I just remembered. I think so in black mechanics, the second law has been changed. We have now the generalized second law, which says that the total entropy of the universe would increase, will always increase, but like a total local region of space may decrease. So, cup of coffee paradox. Physicist John Wheeler so he discovered, so he's the like the founder of black holes. He also coined the term black hole. So John Wheeler realized that if you threw a very hot high entropy cup of coffee into a black hole, the structural messiness disappears from the viewable universe. This creates a massive crisis. It implies you can lower total cosmic entropy, completely breaking the second law of thermodynamics. So this is problem, the cup of coffee paradox. If I throw something into a black hole, the entropy is gone from the universe, which completely breaks the second law of thermodynamics. Now here comes Jacob Bekenstein. So Jacob Bekenstein resolved the paradox by linking a black hole's mass additionally directly to its geometry. Swallowing matter forces the event horizon surface area to expand permanently. He proposed that this outer layer acts as a cosmic ledger recording swallowed entropy has digital information to keep the second law intact. So, uh, what was the case is that Jacob Bekenstein had resolved this paradox by linking the black hole's mass by its event horizon. So if a black hole has more mass, and like a black hole's mass is like still debatable, like how does that how does the singularity have so much mass if it has zero volume? It's like dividing by zero. So there's still, I've still not understood this topic very well, so I'll just try my level best to explain all of this to you. So when a black hole gains additional mass, it also gains the entropy. And to keep the second law intact, what happens is that the black hole projects its entropy on the event horizon. So are you like getting me? Is everyone understanding the topic? Like when we just throw mass into a black hole, its event horizon increases. So it means the event horizon keeps all of those knowledges, the entropy. So, okay, the minimum pixel growth. So Bekenstein used quantum physics to prove that an event horizon grows in discrete steps, not smooth fractions. And because quantum particles have a minimum fundamental size, swallowing one bit of information forces the uh, black hole's boundary area to expand by a tiny irreversible pixel of space. So, isn't this very interesting? Because uh, it says that a black hole stores its entropy on its surface, not in its volume, like because the particles just can't move. The volume, the singularity's volume is zero, so they won't move, right? So uh, and black hole maxes its entropy because it has the maximum number of hidden microstates, and this is also called the Jacob Bekenstein bound. So when if it grows by one, if it gains one bit of information, it would increase by four Planck areas. So and Planck area is like a very small unit, and it's just very good described by the formula that we'll just see. So it means that the black holes store the entropy on their surfaces, and like and this and so what happens is that if anything falls into it, it gains a little bit of it gains a little bit of surface area. So and it also the black hole also disappears, so we'll also talk about what happens to the lost entropy, the Bekenstein bound. The Bekenstein bound calculates the absolute limit for information storage in space. It dictates that the maximum entropy within a region depends strictly on its outer surface area, not its volume. Trying to pack more data passes this geometrical limit of collapse into space into a black hole, the universe's densest storage drive. So, as you can see in the just see in the presentation, uh, the black hole's entropy S is equals to KB Boltzmann constant times C cubed times A divided by 4 gravitational constants times Planck H bar. The reduced Planck constant is also called H bar. So H is just 2 pi 2 pi H. So and H bar is reduced. So H bar is equals to 2 pi H. So Planck constant. So it's very used in this black hole entropy. And if you just want to expand this area, we'll get as we know that the social radius is 2 gm squared, and a black hole is a sphere, right? So we'll get the area as 4 pi r squared, and by just if we just plug in the r in, we'll get about 416 pi g squared m squared divided by c raised to the power of 4. And if we just plug it into the other into just this equation, the r value will get k times c q divided by 4g h bar times 16 pi g squared m squared by c raised to the power of 4, uh, which we'll get as 4 pi k times gravitational constant times mass times gh, which is the gravitational constant and the reduced Planck's constant. And if you just want to represent in Planck, we multiply the upper by 2 pi, which would be 8 pi squared. And like these all are just a constant. So it directly says that mass is proportional, like uh, mass square is proportional to entropy of a black hole, and this is way more efficient than any other. And to get this, we are calculating the number of microstates using quantum mechanics and string theory. Like we cannot just look into a black hole, right? To find the number of microstates, so it has the maximum number of microstates. And as I said, the classical one was like putting a thermometer in lava and checking it, and this one is like looking far away from chimney and deciding its temperature. So this uses quantum mechanics and string theory to calculate the number of microstates and black hole has, and to calculate its entropy. So it isn't linked to the volume inside, but to its surface area. So the bigger the event horizon, the more hidden information it has. Hawking contradiction. Stephen Hawking was shook shook this framework by combining quantum field theory with black hole geometry. If a black hole possesses real thermodynamic entropy, it must also have a real temperature. According to basic thermodynamics, any object with a temperature must radiate energy into space. Hawking mathematically proved that black holes are not completely black. They slowly leak a cold stream of subatomic particles, now known as Hawking radiation. So, as we know about the Hawking radiation, it was discovered by this contradiction which Stephen Hawking gave, that if a black hole has entropy, it also must have a temperature. And when he did the maths, he found out that the virtual particles pairs that were forming in that were popping in out of existence, uh, when they were at the edge of a black hole, one fell down and the other one escaped, and the one that fell down had negative energy, so like uh, minus the black hole's mass, and the other one stole the energy away from the black hole. So this technically counted as the temperature. It's releasing particles, right? So like it radiates very slowly, and there's also a temperature uh, equation for that, but I haven't uh, I still don't understand it pretty well. So if a black hole gets uh, if a black hole loses mass, it Hawking radiation would get stronger and stronger, because the forces at the event horizon get more and more, like to rip them more violently. Like if I wanted to go near a big black hole, I can go and can travel inside the event horizon for a while, because its area is very large. But if I want to go near a small one, I die earlier than the bigger one. So a few new people have also joined us. So thank you everyone for joining us. So the holographic principle. So the holographic principle asserts that the maximum information content within a 3D volume is completely encoded on its surrounding 2D boundary. Instead of scaling with volume, a system's peak entropy is strictly capped by its surface area, meaning our three-dimensional reality may fundamentally operate like a cosmic projection. So, like imagining this is pretty bizarre. I know that. How would you like imagine imagine us on a 2D 2D place, right? So instead, this black hole, it stores its energy entropy inside its event horizon, which is 2D, which is a 2D boundary, and it scales with its surface area. So it increases exponentially more than the other materials other than the black holes. So the Bekenstein-Hawking equation. So this formula unifies thermodynamics, gravity, and quantum mechanics. It proves a black hole entropy S is directly proportional to its surface area A divided by 4 units of Planck area. This confirms that black holes store information directly on their 2D boundaries. So we'll just talk about the temperature formula that he gave. Hawking formula reveals a bizarre thermodynamic truth about black holes temperature. It's inversely proportional to its mass. As it loses mass through radiation, it doesn't cool down. It gets hotter and hotter. Massive black holes remain freezing cold, while small ones burn at raging temperatures before exploding. So as you can see in the temperature formula, it is h plan h bar times c cube divided by 8 pi uh, gravitational constant times kb times the mass. So it's like there are mostly just constants, and if you just look at the mass, it says that it's proportional, inversely proportional. So the larger the mass, the slower it should be, and the smaller the mass, the more temperature it would release. So like and to explain this, we have to just look at their bodies. Like if a smaller black hole is there, what happens is that the force at their boundaries is more than the bigger black holes. So it does it more violently. So if you wanted to travel near a black hole, if it's small one, you'll die earlier than a bigger one. So this is the Hawking temperature formula, and let's just talk about few black hole mergers and take some entropy considerations. When two black holes merge, the total entropy increases consistent with the second law of thermodynamics. The final black hole's area surpasses the sum of the initial areas. The increase in entropy reflects the irreversible nature of the merger process. So, so I know it's pretty confusing that how would it have much greater entropy than the sums combined. So I'll just give you an example. If we have two black holes of the same mass, let's say 10 units. So their total entropy combined would be 10 cube plus 10 cube would be 200. And like in black hole mergers, about 5% of the mass is lost. So our final black hole would be 90 units, and to get the entropy of that, we'll just square it and get 361, which is 161 units more than their parent sums combined. So this is just some mathematics I gave you. So and the final black hole's horizon area also is more than the initial areas. So the information paradox, it arises because Hawking radiation causes a black hole to evaporate and vanish completely. If it displays all the quantum data stored on its horizon is permanently erased, this directly violates quantum mechanics, which demands information can never be destroyed, creating physics' greatest unsolved mysteries. So there's a unit in quantum mechanics called unitary. So it's unique information. So like the elements, the specific molecular arrangements in a diamond are unitary, and if I just throw them into a black hole, what happens? It just gets translated into entropy. And what happens is that we don't get its specific arrangements back, which is a direct violation of this rule. And but there's one more thing called the Don P page. If you have heard about it, so it says that after some times, the some areas in the event horizon, because of the strong gravity, get like are linked, like superposition and entangled. I'll say entangled. They're entangled. So if we have a very powerful radiation coming, if we have a very strong quantum computer catching all of the particles, like not even a single particle should be left, because it will crash the uh, encryption. And if we have that, we can calculate its entropy and we'll get that diamond back, like the specific arrangements. So that is what we predict, which may like not be true, or it may get changed in the future, but this is what we believe till now. So I didn't include Don T page curve here because it could have stretched the presentation a little longer. So let's get into the cosmological context. So the universe's entropy has increased since the Big Bang. Black holes contribute significantly to the total cosmic entropy considerations. influence models of the universe's fate, such as the heat death. As I just said, that black holes are the most entropy efficient, so they account for about 99% of the total entropy. And to get the maximum entropy for our universe, we just plug into the formula, Wittgenstein formula. We get about 10 raised to the power 123. And right now we are at a good 103 or 104 something. So we still have a long way to go, and black holes increase the entropy of the universe by a lot. The starting universe had about 10 raised to the power 88, and a Sagittarius A star has about the black hole has about 10 raised to the power 91, which is about 1,000 times more entropy than the earthly universe. So as you can just say that there are a lot of black holes and the bigger ones which increase entropy exponentially, which means that they account for most of the entropy in the universe. So summary, and like I still did not include a lot of part. Like there's the Claude Shannon one research paper. I did not include that because it's like, let me tell you, it's way too complicated. It's about messages and stuff. The entropy of a message, I think so. It's that, and I did not have enough time, so I couldn't include that in the presentation. It's pretty interesting. I'll try to include that, the Claude Shannon Claude information theory, and I'll try to include that in other presentations. And so let's just get over with the summary. Entropy connects concepts from Clause's steam engines to Hawking's black holes, tracking the degradation of energy, information, and spacetime has the fundamental arrow of time. Entropy derives the universe from order to chaos, framing the grand arc of thermodynamics and information theory. So entropy also leads to the heat death of the universe because of the past hypothesis. Because our universe started at a very low entropy, because let me say that at the early universe everything was uniform, but in gravitational entropy it's being uniform at such small scales is pretty hard. So it's in low entropy, so that's why the entropy of the universe, that the Big Bang decided the arrow of time, because it had low entropy and it's increasing now. So that is why so that is why the universe is entropy increasing. And there is one more thing: dark energy and dark matter. And like dark energy, what I think of it, it's like the universe's way of increasing its own entropy faster and faster. So this is my beliefs. I don't think so I've read any research paper about that. So this is my thinking, that the dark energy, like as quantum mechanics says, that if it does not violate laws, it can exist and it benefits our universe, like the second law of thermodynamics, produce life, because life is more entropy, like they increase entropy faster and faster. So an ocean, like a ocean, gives about tens of times, increases entropy tens of times if it has like living bacterias in it. And this is what I think, because it can exist and it can increase the universe's entropy by a lot, and that too by exponentially faster. So this is what I think of dark energy, as the universe's way of trying to reach maximum entropy, thermodynamical equilibrium, which like in turn is just like the universe's heat death. So this is what I think of dark energy. And we are done with the presentation. If there are any questions, you are welcome. So, uh, hello everyone. Do you have any questions? Okay. Hello, Lakshmi, are you here?
Yes, yes.
So, do you have any questions about this
No,
topic?
no, 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 no.
Okay, so uh, like, do you have any suggestions on which topic should I try next?
You can like entropy is good topic, but like we are conducting this from last 3 weeks. So like I don't suggest any topic, but I would say like if you have any topic that you are interested in and have a good study, you can try that.
Okay, so you're right that we have been studying entropy for like 3 straight weeks, but the thing is that we still haven't explored it whole.
Yeah,
Uh,
yeah, it's a very vast topic
it's a
actually.
bit, yeah. So I also tried like going for optics. I I still did not understand it very well, but I think I'll try optics next. And
Okay.
like I thought of including uh, Shannon Claude information theory, but that was just way too much, and I did not understand the research paper very well. So
Okay.
if I get any chance of making this entropy topic again, I'll I'll make sure that to include the Claude Shannon information theory.
Like you can do one thing for 1 2 weeks you can like include any other topic, and when you get time you can study that topic and make entropy after 2 weeks 3 weeks. Make this session like later, so you will get time properly.
Yep. But entropy is still it
Yeah.
amazes me. It's pretty interesting topic. So that's why I
Yes,
just
yes.
talk about it.
Okay.
And it's fascinating actually.
Yep. And
Someone raised hand, like you can take his question first, we'll talk later.
okay, he's just my father. He raised his hand.
Okay, okay.
Okay. So the thing is happening that I've been trying to make this entropy presentations
Hmm.
and get people like there's one person Satyajit and section they ask questions and like the people in my presentation they don't ask many questions and I take it as like I did not understand I didn't give them a good explanation or something like
No, no,
that.
actually you explain the topic very well, but they don't like generate questions immediately.
Yep, like so there's one person Satyajit. He understand these topics very well, and one time we had a 30-minute long talk about this entropy and stuff. So I just wanted him to join and he wanted him to ask some questions about this. So yeah,
Okay. So, like, I will do one thing. Make a little Google form. Like, I will do it or tell to your father any of this, and I will put it in my community with a good poster. So many people, like, when they fill a Google form, they will wait eagerly for the session. So you will put a notice in a group or mail them directly. So many people can reach you and join the session. It's a formal way, like, so
yep,
we can
nice.
increase audience.
Okay,
Yeah.
so I'll I've
I'll
been
talk with your father, don't worry.
okay. So I've been in touch with one more person, Sarvesh, the Collision of Minds. He's the founder of.
Aryan, so what about the Ramu sir? Ramu sir joined from the USA. Person is right now he is living in Banaras. Ramu, can you introduce sir if you don't mind?
Hello.
Okay, go ahead.
Okay, I think someone wanted to say something like Ishant Khatri wanted to say something.
No, no, I just want to say that session was very well and you've explained every concept very well.
Okay, sir. Do you have like any suggestions on what should I try next?
Suggestions basically, if you have not any other topics to explain, then start from basics. That's if you have interest in space science or astronomy, astrophysics, you can cover from basic like solar system and explain the facts that we normal people not know about the solar system.
Okay. So I was just thinking of that only. I just finished, like, what I did was, I first of the I just explained all the topics very, like, not that on deep, and like got to the quantum mechanics and stuff, and explained
Yeah.
all of that, the quantum gravity and stuff, why there are problems, and started again with the Big Bang. I think so. You were also there, right? In the Big Bang one. Um,
Okay, means I not know that.
okay.
And one more suggestions that you are doing your explanation all from your slides which are written. My suggestion is that you will add something like simulations or images to explore more and to understand more quickly.
I also sometimes try. I uh, I sometimes put them, but it takes a lot of time, and I don't know how to make a simulation, so it's pretty hard for me.
No, if you know simulations, you don't know simulations, then you try with this simple images like you explain the term entropy, then the pictures that shows entropy and concepts related to that. It
Uh,
helps the people to understand more better.
but I just add the text because, like, when the new person join, they can just read the text and understand what is going on there. So
Yeah, yeah. That's also neat, but in some slides, man, one or two slides of that also, in my
okay.
suggestion, my point of view, it should be included.
Okay, so I was also thinking of that. I have joined the propagations some classes, and I just saw people using that style. I'll try that style next time if I got time.
Uh, Aryan, you can use Canva. Canva has good presentation, so you can access images and like good simulations or something else.
Okay, I have tried Canva. Like, I tried to make a title slide, but it didn't work out pretty well.
Actually, na, it's hard to use, but when you like use it properly, it will give a good results.
Okay, I'll try it
Yeah,
more.
and normal images like we are available on Google and etc. You can contact to Lakshmi or sometimes meet, so we can share you too.
Okay. I just sometimes take the images from AI also. Like in my previous presentation, if you were there, the entropy one, I had taken images from the AI of all the equations.
Yeah, I was there. Yes. Right.
Okay, so we are
I will send you one or two PPTs. I have a good samples.
okay.
Yeah.
I think so. We have been over over about 10 minutes. I think so. We should end the presentation. If anyone of you want to say something, you can say it right now. So, should we just end the presentation now? Okay.